Good morning, everyone. Welcome to the John Chappell Natural Philosophy Society. And I am your host this week, Franklin Hu. And today we have Ian Cowan, who normally moderates, but he will be our honored guest speaker today. And before we get started, I just wanted to remind everyone, just a moment here, that our fundraiser for the CNPS is still going on. And we are requesting that if you enjoy our Saturday presentations, that you help contribute and with our fundraiser. And our fundraiser is at the givebutter.com/CNPS 2025. And so if you do enjoy this, we have reached 50% of our goal. So please consider donating. Okay, so let's go back and let's see here. I need to get rid of that. And okay, Ian, so I'll let you get things started here. You'll be presenting us with some slides, correct?
Yes, Franklin. So shall I put the slides up now? I can sort of speak while the slides are up.
Yeah, let's go ahead. Let's get your slides up, and then I'll let you go.
Share screen. Entire screen. Actually, I thought I had the slides up. Share. I put this down. Yeah, can you see that?
Yeah, we can see that.
Yeah, okay, and I hide. Where's my cursor gone? I don't know where it's gone. Sometimes it just locks up.
It's right over there on the right.
It's on the right, is it? Yeah, oh, yes, okay. You're right. Okay, excellent. Oh, okay, well, thank you very much for the introduction, Franklin, and I'm somewhat happy to be in the other chair for a change, so you can listen to me giving my own ideas. Basically, for the last year or so, I've been doing a little research in regard to the perceived value of the speed of light, dependent upon the motion of the observer, or indeed the source. And I've given actually two presentations to Harry Ricker's Sunday morning presentations on cosmology, but I've been working a bit more at it since I did that a bit earlier in the year. And this is a more thorough explanation, both of the observations and also of the theoretical basis. Now, I'm actually following in the hallowed sort of tradition of using classical physics. So you will look in vain for any explanation that I'll give in the next hour or so, which will depend upon the paradoxes of relativity or quantum physics. No, I'm restricting myself to classical means. And in that sense, I'm following people like McCullough and Maxwell and Faraday and Kelvin. Yeah, yes, I am. And indeed, I'm not at all worried if it is said of me what Julius Caesar said of Cassius. Yon Cassius has a lean and hungry look. He thinks too much. Such men are dangerous. Okay, so having said that, I'll go on. So I'm going back a long time, and I'm going back to the Danish astronomer Ole Rømer. Now, he did these observations in 1673 to 6. He'd actually been working in Tycho Brahe's old observatory in Uraniborg in Denmark, assisting with Jean Picard's observations on the eclipses of Jupiter's moon Io there. So basically, in the Paris Observatory under Cassini, they started looking at the timing of the eclipses of the nearest moon of Jupiter, Io. And they said, well, if we could find how the timing differed in different locations over the globe, we'd effectively be it's sort of bringing in a cosmic clock. So basically, I said comparison with those of Giovanni Cassini in Paris should enable accurate determination of longitudes via this cosmic clock. So before the advent of very accurate timepieces, the important one would be Harrison's. They were trying astronomically to be able to indicate to navigators at sea their exact longitude by celestial observations. In this case, the timing of the beginning or the end of the eclipse of Io. Now, this Jean Picard, who was sent by Cassini to Denmark, was so impressed at the exactitude of Romer's observations that he brought him back to Paris actually to assist in Cassini's detailed observations. So I just have a picture of sort of like the very detailed handwritten notes. Most of these haven't been digitized, unfortunately, but he was a very, very precise observer. Now, there are two sets of observations. You can see I've pluralized observations. I've underlined the S there. The observations of Io's eclipses, and also the interpretation given by Christian Huygens. Now, there are two. So number one is done at what is called syzygy, a nice word. Well, that's from the Greek syzygy, which basically means together, yoked together. So, in other words, if you can imagine the sun, the Earth, which is nearer the sun than Jupiter, and Jupiter, you can imagine them in a line. That in two cases. One in which case you have the Earth at the near side of Jupiter to the sun. In other words, they're both on the same side of the sun. And then on the other side, you'll have the Earth on the other side. So the syzygy, and I'll have a diagram about this in a second, determinations allowed the true period of the orbit and timing of the start of the eclipse. It was found to be about 42 and a half hours, the period of the eclipse of the moon Io, and 22 minutes difference between the near and far points. So the textbooks just say, well, look, when the light from Io, reflected from the sun, travels the Earth, and the Earth is on the near side of its orbit, it takes a certain amount of time. It's on the far side, it takes longer. And it was found that it took about 22 minutes longer. And he attributed that to the extra time that light took to traverse the diameter of the Earth's orbit. I'm basically just quoting from what the textbooks say. And he got something like, I'm basically in this thing C0 rather than just C, because I'm emphasizing that it's in a vacuum or in the ordinary ether. We might, if we took it in a medium. He got a value of about 27% lower than today's value. Now, I was pondering, this is a bit of an aside, but I was pondering on this because we know that it takes about 16 minutes longer to traverse the diameter of the Earth's orbit. It takes 8.3 minutes to get from the sun to the Earth. And then if you take the diameter to be, the orbit to be roughly circular, it takes twice that, 60 minutes. So the textbooks say, that was really wonderful that he took it to be 22 minutes, and yet it's 16 minutes. And that's why he got a 27% lower value. But that didn't satisfy me, because Romer was undertaking most accurate determinations. I mean, to within seconds. So a difference of 6 minutes in 16 is a very large difference. And I was trying to ponder what the difference might have been. And I've come to a provisional explanation that it might be the inaccuracy is due to the difficulty in distinguishing eclipse from occlusion. So in other words, when you're looking at the moon, which is going into the shadow of Jupiter, particularly when the Earth is at the far side, you might confuse when the planet actually goes behind when the moon goes behind the planet, it's actually occluded. Occluded is the correct technical term, and it actually enters the shadow a little later. So it might have been hard to distinguish those. Anyway, that's a bit of an aside. The second set of observations are not in the textbooks. They're at quadrature when the Sun, Jupiter, and the Earth subtend an angle of 90 degrees, or there could be positive quadrature, negative quadrature. Positive quadrature 90 degrees. Excuse me. Negative quadrature is 270 degrees. Now, from this, Romer determined a variation in period, 42 and a half hours period of the eclipse of around plus or minus 15 seconds. I did say that these timings were very, very accurate, not minutes, seconds. He actually did this from averaging multiple observations because it was really impossible to get such accuracy from a single observation, depending on whether Earth moving away or from or towards Jupiter. This is not in the textbooks. So you may say, how did I find this? Well, I'll tell you that when I've given you the second the second diagram. The first diagram is a syzygy observation. So you can see that when the Earth, Sun is there, when the Earth and Jupiter are on the same side, you evaluate the timing there of the start of the eclipse, and when it's on the far side, you do that as well. It's actually quite difficult to do these observations because the Sun tends to obscure Jupiter. So you're doing it very near to the time of sunrise or sunset. But anyway, so if you get something like D is the diameter of the Earth's orbit, you just get C naught, which is the value of the speed of light in free space, is D divided by delta T. I call it delta T minus, which is the difference in timing. This is what 22 minutes obtained by Romer. It should have been 16 minutes. So but he also determined the true period of the eclipse. So when you're in a line, you can actually evaluate very accurately the true period of the eclipse because the Earth is not moving away or towards the Jupiter. It's actually in line with it. Now, but this is really the interesting one. This is 3 years later. So yes, 1676. Now, and this is not shown in the textbooks generally. So here's the Sun. Here's Jupiter. Here's Io. I haven't actually shown it, but Io is moving around it, and it's entering the shadow of Jupiter here, which is caused by the Sun's rays being blocked by the disk, of Jupiter. Here's the Earth. So the Earth is going from F to G. And by the way, there's the syzygy. These are the syzygy points here. Sorry, that's these when it's in line. And it's in quadrature here when there's a right angle between there. But if you just expand, this is not really to scale. If you expand it, the Earth goes from F to G in the period of the eclipse of the period of the eclipse of Io. And it also, when it's on the other side of the orbit, it's going from L to K. It's moving away. It's moving away. Now, I might just mention how I got this. So I came across a number of years ago in a paper by Roberto Monti. I think many of you are familiar with him. He's an Italian physicist, and he had a paper sort of analyzing and criticizing relativity. And he refers to this. just briefly, and it was sort of new to me. And I looked at the reference, and the reference seemed to be to a Russian academician by the name of V.I. Sakharin. I looked up how the pronunciation should be in Russia, and I think I'm not too far away. Skkerin. And I got hold of quite a tome that he'd written. It's online, actually, on actually, he's not mincing his words, on relativity being a hoax. And he's analyzed these. Now, Sakharin and Monty's analysis is not quite the same as mine. It amounts to the same. Mine brings in a gamma factor, the Lorentz factor. So in other words, I use the expression that when the Earth is moving towards the Jupiter and Io, the eclipse actually should be slightly less in time because you're moving towards the light rays coming towards you. And here it should be further because you're moving away from it. So this is the shorter period, and this is the longer period, and the delta t minus is the difference. C naught t naught is the distance it would it travel from the time that the Earth is moving, the initial point that you would take. So if you solve that, you get that. As I say, the expressions used by Sakharin don't bring in the gamma factor, but I'm bringing this in because I've brought in something that I think is reasonably novel. It's an analogy between these experiments where you have an observer moving towards a source of light, and you're getting a different period. Now, you see, I say that were special relativity to be true, well, the speed of light is invariable, irrespective of whether the observer is moving away or towards. So delta t minus is zero, and this business there's no c naught minus. It's c naught there. It's just t naught. It's t naught all the time. You see. So, but these experiments were done, and it appears that he got some sort of difference. It was only a matter of seconds. It might have been 30 seconds difference between the two, plus or minus 15 seconds. But the interesting thing is that this is not discussed in any textbook that I can see. So the quadrature observations of Romer. Now, Bradley, the next thing I've pointed out is the English astronomer Bradley, who discovered aberration in 1727. Actually, he was looking for, what's the word? My mind has just gone. Parallax, but which is a much smaller effect. But he discovered aberration in the meantime. So very, very strange. This entails the use of resolved Earth transitory and light velocities, and it's equivalent to the Galilean composition. So he measured C naught to within 5.5% of the present value. Very, very accurate. Now, you can do a lot of algebra with these things, but if you just apply the law of sines, whereby the side of a triangle opposite the sine of its of the angle opposite is basically a constant for the three sides of the triangle, you can get that. And that's very, very accurate. It's based on a composition where the Earth is moving at speed v in this direction, and here's the star. Sorry, the real position of the star is here, and the light is coming down at c in a period t. It goes vt and it goes ct. This thing. The star's apparent position is tilted forward an angle theta dash there, or theta prime. So the difference is that there. You see a new bit of geometry. It's totally Galilean. And another point which is worth emphasizing, it's not a reciprocal phenomenon. So in other words, if not the Earth is moving, but the star is moving, you don't get it. So for example, this has been shown in observations of binary stars where the stars are moving at different velocities. You get exactly the same aberration Whereas relativistic derivation says that no, you would get different because it's only the relative velocity which matters. But in actual fact, no telescope motion during the light passage through it leads to no aberration effect when the star, not the observer, is moving. Again, if I'm indicating to you something which is obvious or something to be questioned, whether it's one or the other, this is not mentioned in the textbooks. It's glossed over. It's glossed over. It may be a bit too embarrassing. So there's a very accurate determination of the speed of light by Bradley in regard to aberration, stellar aberration. Now, then we come to much further to the Sagnac experiment. And I'm taking these elements because I'm trying to bring them all together. In a moment, you'll see that. The Sagnac experiment of 1913, it measured a fringe displacement in counter-rotating beams, which was determined by the speed of the disk, which is typically 0.07 of a fringe shift for a speed of around 2 revolutions per second. Now, if you think about this, the traverse path at the vacuum speed of light, C0, varied in length as viewed from the lab frame, because the detector was either moving towards the light which was moving or moving away from it, or the speed of light varied as viewed from the rotating frame. So in other words, frequently you'll say, oh, the explanation for Sagnac getting a positive fringe shift is quite simple. You have different lengths of the traverse path. That's only from the lab frame. From the point of view of an observer on the disk, you're getting C plus or minus V. Yeah, simple as that. If you work it out using this ordinary classical mechanics, you get delta T minuses 4A. A is the area, the surface area of the disk. Omega is the angular speed, and C0 squared is the speed of light squared. One other thing which is interesting is that two French physicists, Dufour and Prunier, in 1942, did some ancillary experiments based on the Sagnac principle, where they reflected the light intermediate between its emission, by the emitter, and its reflection back to the emitter for detection. They reflected them at mirrors on walls and the ceiling of the laboratory and so on and so forth, and they found no difference. So this indicated that the light actually, contrary to some views that have been expressed by dissidents, doesn't take up the spin of the disk. It continues to travel in the Earth's frame, the Earth's etheric frame. It made no difference when it was the light was transmitted or reflected from different mirrors and all over the laboratory. Again, this experiment is not well known at all. It's actually almost a secret. And again, there are some ideas. It might be said, well, Dufour and Prunier did these experiments when Paris was under German occupation, and maybe the papers couldn't get out. Yes, but that doesn't explain for the last 80 years why the papers never got out. So I just like to point that out to you, that the speed is varied on the surface of the disk, and also it's traveling in the Earth's ethereal frame. Now, by the way, people sometimes come across the dismissal of all this to say, oh, things are constant, the light is constant, and these are just observer ideas. Well, that is true with regard to any speed. I mean, if you have a motor car which is driving at 50 miles per hour down a motorway, that speed, the speed of the wheels relative to the highway, is constant. That's true. Nothing's changed that. However, if I'm in another motor car moving towards it, if I'm moving at 50 miles per hour, moving towards that motor car, it's ridiculous to say the speed must be constant because you're not changing anything. The relative speed is 100 miles per hour. You have to add the two speeds together. That's true, yes. And you cannot dismiss it by saying the car is still doing 50 miles per hour relative to the road. Same thing. The light here is going at C naught relative to the laboratory, but it's going at C naught plus or minus V relative to the observer on the disk. Now, so I've now described 2 experiments of the 3 of the triad that I'm going to try to bring together. The third one is the Michelson-Gale experiment of 1925, and they measured a fringe displacement averaging about 0.230 in counter-rotating beams through a piping some 1,850 meters in perimeter, determined by the speed of the daily rotation of the Earth at the site, which was in Clearing, Illinois, about 350 meters per second. And again, looking at it in a similar way to the way we looked at the Sagnac, because this is a Sagnac interferometer, which is basically just moving on the Earth's surface. It traversed a path at a speed c naught, which varied in length as viewed from outer space, from an outer space frame, or the speed of light varied as viewed from the Earth's frame. So that it's true that from the outer space, the distance between the emitter and the observer was varying. But from the point of view of the Earth, where you're actually moving, that distance wasn't changing, and therefore the speed was changing. You're getting V plus or C naught plus or minus V. And again, if you just do a little analysis, which is quite consistent with classical analysis, you get delta T minus is 4a omega over sinus. Here the sign of the latitude comes in, because you have to project this onto the equatorial plane, basically, and you're getting it vertically from the Earth's surface. I might just mention one other thing here is this is, as many of us know, a first order effect. What comes into the equations based on Sagnac, and these, by the way, are one-way speed of light measurements. Frequently said, "Oh, it cannot be done." Well, here it's been done. It was done in 1673, but yes. So these are dependent upon V over C, which is the first order effect. If you try to do two-way light speed analyses, it's dependent on the square of that, V squared over C squared. So it's a second order effect. If you work out the equations, say a Michelson-Morley and that. So so that's why the MMX requires very, very great accuracy to discover anything at all, any variation. We know that there isn't a sufficient variation to underwrite the speed of the Earth through the ether, if you like, which we know to be 30 kilometers per second if we take a stationary ether. Basically, the ether seems to be rather largely dragged by the Earth, and that is true for any large gravitational mass. It isn't true for the Sagnac disk because it's too small a mass. But nevertheless, that very small difference. Here we're noting the non-dragging, or the slipping of the Earth through the ether in its diurnal movement, in the same way as the Sagnac disk is slipping through the ether. It's not actually carrying it with it. The same the Earth in its spinning, in its daily spinning. But in 1964, they started doing Michelson-Morley type experiments. It was people like Jaseja and Towns. They did experiments using lasers in these sort of cavities, these resonant cavities, and using etalons and using things like interferometers. Well, a very accurate one was done in 1979 by Brie and Hall using a Fabry Pero interferometer and a Nettelon with a laser resonator. And they published the paper, which is available. You can get the paper, and it says we haven't departed from Lorentz. What's the word they would use? Lorentz covariance, yeah. So that the speed of light wouldn't change dependent upon its direction. However, some further analysis has been done with this experiment, and it was found that they had actually experienced a 17 kilohertz signal, which seemed to be very, very strange. It was much smaller than anything they would have expected had the experiment proved positive. And they dismissed this as spurious, maybe due to some other interference, vibrations or something. But if you analyze that 17 kilohertz signal, you find that it actually shows up the spin of the Earth at the location. I think it was in Colorado. It was a higher speed. It was a bit higher than 350. I think it might have been 500 meters per second. It was nearer the equator. But so there's an example of a Michelson-Morley experiment showing up the spin of the Earth and some motion and so on. The difference in the speed of the Earth, in the speed of light in one direction versus the speed of light in a perpendicular direction. Now, so here, what I've tried to do, just better watch the time, we're halfway through. What I've tried to do is I've tried to put the three of those alongside each other. The first one is the quadrature observations of Rome, where the second one is the classical experiment of Sagnac, where he claimed to have disproved relativity and established the existence of a luminiferous ether. And following on from that, the Michelson-Gale. The Michelson-Gale people, of course, I don't know whether they were political or they were good scientists, but they said, oh, this can be explained in terms of relativity or in terms of classical physics. I would doubt whether it can be explained in terms of relativity. You have to make some quite severe jumps of imagination. By the way, this circuit here was just what they called a fiduciary circuit. So the area there, enclosed area, was so small that you would get no effect. But when you have an area, this is like 2 kilometers perimeter, you do get this figure of 0.230 fringe shift. Anyway, so I say all the preceding apply for observer motion relative to a static source. So if you think about that, in the case here, if you take the light being generated by Io, it's reflected, of course, but it's generated and sent towards the Earth. The Earth is actually moving towards that, that system of a medium there where the light is being moved, and similarly here you're generating light, and the detector is moving either towards or away from where the light was generated. In this case, in the Earth's ether, and here it's exactly the same, except the Earth is actually causing the spin. But I say, therefore, Einstein 2, which is the second postulate in his 1905 paper, that the speed, if you read the actual words, said the speed of light, I think this is the velocity. It's usually translated as the velocity of light is independent of the velocity of the source. That's what it says. That's actually correct. The speed of light is independent of the speed of the source. But I say, so what? It's a truism, which is true for all kinds of waves. If you think of water waves, or if you think of seismic waves in the Earth, it's actually independent of the motion of the medium, because it's actually traveling in the medium and it's caught in the medium. It's only later in the paper that it appears to be that Einstein moves towards reciprocity, where he says, well, if the speed of light is is constant, independent of the speed of the observer. It must be constant, independent of the speed of the source. He doesn't actually say that in so many words. Later people do. And all the physics textbooks, my undergraduate physics textbook said that. They didn't say the speed of light is independent of the speed of the source. They said the speed of light is constant, independent of any motion at all. They've gone further, because at the very beginning, Einstein, in deriving the Lorentz transformations, actually uses c plus or minus v. So he doesn't appear to be considering reciprocity in the early stages. So anyway, Romer and Sagnac, Michelson-Gale experiments are analogous regarding Galilean composition of speeds. So I think that that's a bit of a new thing that I've introduced. I've looked at the same equations underlying the three of those, and I'm getting basically the same results as other writers have, but they haven't actually amalgamated these together. Now, just one or two slides, or three slides maybe, on the theoretical basis. So another thing I've been looking at is what are called total derivatives, which are always used in fluid dynamics. If used by analogy in electrodynamics, provide a wave equation including a convective term. So you have the Nabla squared. Now, U could be the density of a fluid, or could be the pressure. It's reliant upon the three spatial coordinates x, y, z, and the temporal coordinate t, 1 over c squared. My cursor just disappears at certain times. Here it is. But here you have the additional term v dot, the dot product of v and the gradient operator, all squared. That's well known in fluid dynamics. It's always used. Whether you're using the Lagrangian analysis in fluid dynamics, where you're looking at a particular position in space and you're seeing how the properties of the fluid vary at that space, or you're using the Euler system, where you're looking at the history of any particular particle in its motion through the fluid, you use total derivatives. It's very, very strange now that one raises the question why it isn't used in electrodynamics. And I say this obviates the necessity of using Lorentz rather than Galilean transformations to preserve invariance, because Lorentz transformations do preserve invariance, but they're really an artificial, I call them a trick, actually. They're a trick to preserve invariance. What equations would you need to preserve invariance if you admit the total derivation, the total convective term, v dot nabla? And thus, you're back to the simple two-way speed addition, where if you had, as I say, the motor car going at v1 and another motor car going at v2 in the opposite direction, the relative speed is v1 plus v2. Rather than the artificial, I say, Einsteinian one, which is v1 plus v2 divided by 1 plus v1 v2 over c naught squared, which will preserve the constancy of c naught whatever happens. So in other words, you're not able to amalgamate any velocity with c naught. You still get c naught. So that's one of the theoretical bases. Now, so a little more turgid here. Lorentz versus Galilean invariance with partial derivatives. So if you take the Maxwell equations with the electric and magnetic field intensities, and if you do the usual analysis, and I'm amazed that Maxwell did this without the modern vector notation we have now, because by putting in the vector identities you can get this fairly quickly, but it's a bit more ponderous to do it without that system, which was introduced, I suppose, by people like Heaviside, because Maxwell was using quaternions. But anyway, you get a wave equation, and I'm just putting the operator in. The second partial derivative with respect to time equals c naught times the Laplacian, basically. I've kept you could put E in there or you could put H in there. I've kept those out. I'm just using the operators for simplicity. And for further simplicity, if you take, without loss of generality, I suppose, the x direction to be the only direction. So the velocity has only an x component, y and z disappear. And for planar waves, you get the one-dimensional wave equation there. Now, if you take the Lorentz transformations, x dash gamma, x minus ut, and t dash is that. And by the way, you can go to Galilean transformation, which basically means that gamma would be 1 and C naught in this expression would become infinite. You get the usual x dash is x minus vt and t dash equals t. Well, if you use the chain rule here, bit of algebra, calculus here, use the chain rule in transforming the partial derivatives. You get the Galilean transformation and it's not invariant. You get this expression with cross terms. And if you use the Lorentz transformations and you substitute those in there, you get invariant. But you've had to pay a very big penalty because you're back at the same C naught that you started with. So C naught hasn't changed. And you can factorize that into this here, just the difference of two squares. And the solution is that. So it's independent of V. What a surprise. You think it's actually moving at V and it's convecting through the fluid and it's irrelevant. Well, I think there should have been some warning signals here already. And it's only that we have such an edifice of modern physics with relativity and everything which is based thereon that people are not seeing that. Let's have a look at the proper derivation, or so I say. I say Galilean invariance with total derivatives. So I use the Stokes notation, the notation which is introduced by Stokes, that we move from the partial time derivative to capital D by dt, which is equal to partial time derivative plus v dot nabla or v dot del. And you put them in the Maxwell-Hertz equations. Now, by the way, I'm calling it Maxwell-Hertz because Hertz was probably the earliest to propose a modification to Maxwell's equations using the total derivatives. So I'm calling them Maxwell-Hertz equations. And if you do that, you get this for the wave equation, again, in operator form. And again, I'm using the planar wave, and you get that. You have to add this V times the partial differential. If you expand that out, you get this, and you expand it out and get that. And that can be written there if you just take this bit out, difference of two squares, and put it in this bit, and so on. And that can be neatly expressed as that. And this time you get the solution x minus C naught plus Vt and x plus C naught minus Vt, which is what you would get in fluid dynamics all the time. And that's a more rational explanation. So from that, I'm inferring that the Lorentz transformation is a trick to try to obtain invariance when you use only partial derivatives in the Maxwell equations, as Maxwell himself did originally. It's an adjustment tool. And you're paying a high price for it, by the way. You're paying the price that the result is independent of whatever velocity the electromagnetic field is experiencing, which orthodox physics would say, of course, that's normal. I say that's a very high price. It's against common sense. And if you just introduce the total derivative, you get this C naught plus or minus V into it. Now, just very quick, I'll move quickly maybe through this because we're paying a bit of time. And I'd like to have plenty of time for the discussion. Doppler equations, classically in the Doppler transitions operating in a medium, which could be a fluid or ether, again, an analogy, there is a non-symmetry between source and observer motion, which is not what relativistic physics would say. So for purely source motion, both observed frequency f and wavelength lambda vary while wave speed remains constant. So again, that's another way of looking at it, that when the source is moving in the ether or in the fluid, c remains constant, but the other variables vary. F varies all the time, by the way. For purely observer motion, both observed frequency f and wave speed c vary, while wavelength lambda remains constant. If you think about that, you can see how that works out. But the important thing is that frequency always varies. But here, the wave speed varies, and it doesn't matter whether it's electromagnetic radiation in the ether or a speed of a fluid, speed of a particle in a fluid motion. It's the same thing. Once the observer moves, you get a difference in speed. You can work out the equations here. The classical is basically this, and the relativistic one is this, because you see, VO is the speed of the observer, and VS is the speed of the source. But it's only the relative speed V which matters in relativity, which is the difference in speed between the two, VO minus VS. Now, if you move them at the same speed, and you do two experiments, in one case you move the source and you see the difference in frequency change, and in another case you move the observer and you see the difference in frequency shift. Well, according to relativity, there's no difference because V is the same in both cases. So delta FO over FS is 0. However, if you use the classical the hydrodynamic equation, basically I call it that, you'll get a difference, because you can see that C naught plus V is not the same as 1 over C naught minus V. And if you expand that out by the binomial theorem, you get it's of the order of beta squared, where beta is V over C. So one possible experiment would be that if you had radar equipment transmitting at, say, 10 megahertz, and which can discriminate to 10 hertz, in order to pick up this difference, the ratio being thus 10 to the minus 6, the speed of the relatively approaching object would have to be at least 1,000th of that of light. So the experiment, while quite feasible in principle, would no doubt be costly, requiring things like orbital satellites and much higher precision equipment. So in other words, if you could get this experiment, which I think would be a cosmological one requiring satellites, you could see whether delta FO observer over FS equals 0, or this very small difference, and that would satisfy whether special relativity is right or wrong. But nobody would do this experiment. They would say, well, even if we were to ask Mr. Elon Musk to do it, and he's very much wrapped up with politics at the moment, but even if we could persuade him to do it, it would be a waste of money, because we know relativity is right. We know the result. Now, there have been subsequent validations, yes. There have been subsequent validations of C naught plus or minus V, which is heresy. It's heresy to modern physics. Brian Wallace in 1969 analyzed a considerable amount of data which had been assembled through experiments undertaken in the MIT Lincoln Laboratory of Venus ranging. This was started, I think, in 1961, and there was a lot of observations there. Now, Wallace, he presented a paper actually to one of the STG, Space, Time and Gravitation conferences, which were held in St. Petersburg, Russia. He attended one, I think, maybe in the 90s, maybe in the fairly early 90s, and he gave a paper. I attended one in 2004, and I gave a paper at that as well. I don't know if they're still running, actually. His was maybe the third, mine was the 7th STG conference. But anyway, he's reanalyzed this, and he claimed that what was staring people in the face, if they only had the wit to look at the data, was the fact that when the Earth in its orbit was moving towards Venus, it in contradistinction to when the Earth was moving away from Venus, you got a different measurement of the speed of light. And it was basically dismissed. So that's the Wallace analysis. GPS, of course, employs the Sagnac correction for Earth rotation. Now, the late Al Kelly had some correspondence with the CCIR, which is the International Committee on of the ITU. I don't think it's called CCIR now. It's the French acronym, the for radio, and because some of their publications said, "Oh, this is a relativistic correction," and he said to them, "It's not a relativistic correction at all, because if you had any relativistic correction, it would be orders and orders of magnitude smaller. You know, it might be 10 to the minus 8 or something small. This was a major. And if they came back and they sort of reluctantly said, "Oh, well, you are right in theory, but it's all to do with relativity, so we use relativity." Anyway, GS employs the Sagnac correction, which on the face of it, maybe to a man from Venus or Jupiter coming down without any preconceived ideas, would say that contradicts the special theory of relativity. But people now who are so used to defending relativity find some way of, explaining it away. Now, the third one here is the Rudyong Wang et al., a Chinese gentleman, in 2004. They and his colleagues have demonstrated the linear Sagnac effect with a conveyor and fiber optic gyroscope. So here, using fiber optics, so instead of using mirrors to reflect the light in opposite directions around a spinning disk, that had to be done with technology that we've had before optical fibers. But you can now bend an optical fiber, and you can have it, by total internal reflection going around, and you can basically have the majority of a circuit linear, and you can just have a very small section around here, just to bring it back into the opposite direction. This is going at V, and this is going in the opposite direction at V, minus V, optical fiber. And you have a fiber optic gyroscope, which is basically, emitting the laser light, and is also receiving the laser light. So you can see whether there's any interference fringe there. So it's a modern Sagnac experiment, but it's working in linear because the fog is actually moving with the FOC, fiber optic gyroscope, fiber optic conveyor. Okay. And because again, people have said, "Oh, you cannot even talk about the Sagnac effect of 1913 in terms of relativity because it's non-inertial. Special relativity only applies to non-inertial systems." Well, it's funny how special relativity, which is meant to be a more exact application of dynamics than Newton's system, suddenly breaks down when you have a little spin here, whereas the Newtonian classical analysis works very, very well. But anyway, this has given the lie to that excuse, because it works exactly in a linear fashion as well. And the only purpose of the wheel here is to bring it back in the other direction. So there. And by the way, the expression is the same. It's 2LV over C naught squared, where L is the perimeter, the total perimeter of the circuit. Okay. Now, so I say that as for other wave motion in a medium, all other wave motion, without exception, the speed of propagation is independent of the motion of the source, but not of the observer. And this has been well established experimentally. So in other words, once the disturbance exists in the source, in this case light produces a wave in the ether. Well, it doesn't matter how that source is moving. It's actually captured in the ether, and it's the stillness of the ether or the motion of the ether which determines whether the light speed is whether there's any change from its initial position or not. And I say that this is consonant with analysis using classical theories of dynamics and the kinetics of fluids. So, we're just applying analysis which has been proved to be more than adequate in all other areas of physics. And it's unfortunate that in electrodynamics we've missed this, but it has been brought back in some other ways. Now, as an afterword, and this is my last slide, abuno disce mines. So one is quoting from Virgil's Aeneid here, where he says that from one example, learn everything. From one example, learn everything. So a few weeks ago, we had a talk given by James Aratoun on the work of the Irish physicist or academician Alfred O'Rahilly, who wrote this 900-odd page book, Electromagnetics, in 1938. And this is well worth delving into. It's highly technical in some aspects and highly critical of relativity and quite analytic. Well, O'Rahilly quoted in the book a popular extract from a popular work called Science, A New Outline by a contemporaneous author, J.W.N. Sullivan, in 1935. And he said, suppose we are at rest in what? And that we are passed by an observer traveling with half the velocity of light. We send a ray of light after him, which we observe to overtake him at the rate of 93,000 miles per second. Okay, half the velocity, half the speed of light. Our statement asserts, these are earlier statements made, our statement asserts that this observer, when he measures the velocity at which this ray is overtaking him, finds it to be 186,000 miles per second. These statements are so opposed to common sense that they sound like sheer nonsense. To which Alfred O'Rahilly responds, not only sound like, but really are sheer nonsense. So thank you very much for your attention. And I hope I wasn't speaking too quickly, and we can go into any of these details further if necessary. So I'll leave the matter at that for the present and hand back to our moderator, Franklin. Thank you very much, Ken.
All right. Well, thank you very much, Ian, for that presentation. So I had a few questions. So like the first one that kind of came up in the chat is that, I've heard about this attempting to measure the speed of light by looking at eclipses of like Io or Venus. Although I must admit, I still have no idea how you could possibly do that. I mean, if you have Io eclipsing behind Saturn and measuring, I don't say how long it takes for it to disappear and when it reappears, I'm imagining that's going to be constant no matter whether you are heading towards Saturn, away from Saturn, looking at it left or right, or any of the quadratures. So maybe you could clarify that. So that why, how on earth can you tell the speed of light by looking at something that? I mean, did they even have clocks that were accurate to 30 seconds over, say, a 6-month period? I mean, even our digital watches are only accurate to a second for every month. So how could they, back in the 1700s or 1800s, have clocks that are even accurate enough to make those determinations?
So you're talking about the Romer experiments Franklin. And
Yeah, the first ones you
the
brought
two sets of experiments, the syzygy experiment and quadrature.
Yeah, I don't understand.
Or are you only asking about the quadrature?
No, I don't understand how any of those experiments could actually work.
Okay.
Based on just
Well, you can,
observations.
okay. Well, yeah, it's a bit difficult to see this in the quadrature case, and we can come to that in a second. But I think the syzygy might be quite simple, because if you can imagine that he's looking at this moon, which is orbiting Jupiter, and he sees it goes into the shadow at such and such a time. And this is where the Earth is the near side relative to the planet. And so they worked at these tables when the eclipse should start, right? It starts such a time, and they know the time of year, and they know,
so how do they
exactly. They've got this tabulated. And then,
I mean, that's my question: is that
observation?
They know exactly, well, all you can do is you can look up there, and you can see things happening, and that's all you can see. Then, I mean, if you had a clock and you knew that precisely the eclipse happens at 12 noon every day, then you could make a measurement like that. But it's like, well, there's no clock over there in EO. And you don't know exactly when to expect the eclipse to happen. But or maybe it works that you just take all these observations and you just observe the differences, I guess, and then maybe presume there is something that's different. I mean, I don't know what would actually be different. I mean, if the eclipse happens for like 30 seconds or something like that, I mean, does it take like 40 seconds or 15 seconds in different positions? Is there something different there? Because I would suspect that no matter where you observed it, the light.
No, let's because you're amalgamating all these things, which is fair enough. But let's try to separate them for the second. Let's take the simple case first, and let's just try to analyze that, Franklin, and then we'll go to the more complex one, which you're talking about. The quadrature observations, all that. Take the simple case. This gentleman has done detailed experiment. Cassini actually has done more cataloging exactly when the eclipse occurs and how long it takes and when. So they have tables. They know, just like we know, when the next eclipse of the moon should be, or we know today when the next eclipse of Io should be. We have very detailed tables. They had very detailed tables hundreds of years ago. But they found that the eclipse occurs earlier when the Earth is nearer Jupiter than when it's further. When it's farther away, it occurs later. Okay? So they knew that. They say, we're expecting the eclipse to occur now.
But once again, back in those days when they barely had spring watches, how could they possibly time the eclipse to a 30-second accuracy? That, I guess, I find that hard to believe.
No. You're doing what I asked you not to do. You're coming to the second bit, which is 30 seconds. Let's come to that in a second. Let's get the first point established first. This is 20 minutes. It's not 30 seconds. It's 20 minutes. It occurs 20 minutes later. 22 minutes later, he calculated. It actually occurs 16.6 minutes later, actually. It's twice 8.3 minutes. Because the light from the sun.
I mean, I could believe that. I mean, if they were.
Why is it the start of the eclipse?
At 12 noon, and then they observe it happening at 12:15,
Yes.
Then I guess you could do that. Although at that point, I still kind of doubt that they could time an eclipse to even half an hour's accuracy.
Okay, that's all that there was to the first series of observations. That's all there was to the first series of observations. The eclipse was occurring, according to the books anyway, 22 minutes after they reckoned it should, because they knew the period of it and they knew exactly, when it normally occurred. So,
Yeah, I think maybe
how
it's
do you explain
helpful
that?
when
Well,
you get
they
that,
say that represented the extra time that it required for light to traverse the diameter of the Earth's orbit. Okay, so if we take that now, the second series of observations, that's where it's a little more complicated. You're right to be raising these, and the textbooks don't say anything about this because they don't actually have it. But what you're doing there is, if you're using what I would say is common logic, which is used in all other areas of physics, you would say that we've measured the period of the eclipse. We know that. We know the period of the eclipse when it's in syzygy or in quadrature. Now, when the Earth is moving towards Jupiter during the 42 and a half hours of the eclipse, well, the eclipse will be a little less in time than 42 and a half hours. And if it's moving away from Jupiter during the 42 and a half hours, it'll be a little more. Now, it won't be minutes more. It'll be a tiny fraction more, because the speed of light is so great in comparison with the speed of the Earth's approach or recession. But there should be a difference measurable. Now, if you accept the special theory of relativity, there should be no difference. It's zero. It's absolutely zero. Okay, you can see that, can you? Okay. So, and if you plumb into the equation, if you plug into the equation these rough values, you'll find that it's plus or minus 15 seconds, roughly. Now, you're right to question whether that could be measured in those days. So what they did is they had multiple observations. They had 30, 40, 100 observations, and they averaged them out. And they found that, yes, when the Earth was moving towards Jupiter, it appeared to be maybe very slightly less time in period, and when it's moving away, it's slightly greater time period. So what I'm saying is the data have not been analyzed maybe in sufficient detail digitally, but it appears that it's a non-zero value, and it would have to be zero were SRT correct.
I mean, would it? Why would it be zero?
Franklin is asking how time was measured back then. I don't know if you are you? Yeah. Is it only that? James said you were just asking how time was measured. James in the private chat said all you're asking is how time was measured back in the 17th century. I don't think it's only that you're asking, is it?
Well, I mean, I have my doubts. I'm surprised that they could make such measurements. Now, perhaps I think they could have measured like how long the eclipse took accurately to within seconds. They could do that, but over, like, say, 6-month period, I don't think that they could track it for very long, for that long. Was kind of my question. I just don't know how they managed to do that. That would be remarkable if they.
Yeah, I mean,
to do that. So just some clarification. But I think
Jim, I think has put it quite well here. He says, was there statistical significance of the quadrature difference? Well, I'd have to concede probably not. No, because of the errors of measurement and the very small. You'd have to do this, but I don't think you need to do that, because you have a lot of data, more modern experiments, very precise, which are giving. All I'm saying is that the experiments which were done hundreds of years ago are consistent with the difference, with the consistency of there being a non-zero difference.
Yeah, and there's a non-zero difference, so
we could get very much hung up.
I mean, or are we considering?
We could get very much hung up on these early experiments and talk about them, whether they meant anything or not. But they're just part of a pattern, according to my analysis.
Well, I mean, is that pattern? I mean, we're talking about, this whole effect of the eclipse, isn't that just a gigantic Signac effect because everything's moving? So that's why we would expect
Well,
there to be.
that's exactly my point. That's exactly my point. Yeah.
Yeah, is that your point that this is just a gigantic Signac?
Yeah, and I'm almost claiming to be the first person to have put that out, but you've said it now as well. Yeah,
Yes.
it could be considered a sort of a large Sagnac instrument.
But are you saying that? See, in the comments here, we're getting some things about some people saying the Signac effect is like a relativistic effect, which is like I don't know what you think about that, but that seems I don't think that's right. Is that an example of the relativist?
I must apologize, as I have done before when I've spoken, that I haven't been looking at the comments. I'm trying to listen to you and look at some of the comments here, but I've missed them. I'm not surprised that people who believe in the orthodoxy of modern physics would say it's a relativistic effect. We can discuss that. No, I don't think it is either. I agree with you there, but
yeah, there haven't been a whole lot of comments, but it's just interesting that you're talking about the Signac effect. And I was thinking, and you mentioned this linear Signac effect, and I was thinking about that, and I was thinking the better way to do this would be to measure the speed of light, but having a fixed, in order to measure speed of light, typically you have like a fixed distance, like 10 feet or something, and you're trying to measure how long it gets from one end to the other, but in Signac, it's effectively like you're having one end of the measuring thing moving at all times. So that would be a linear explanation that if this detector is moving constantly in a velocity v, then of course you would measure a different velocity. And that would be kind of cheating because you're not keeping the distance that the thing is traveling at a constant, right? And that's what Signac is doing. Essentially, is that you're moving the detector closer to the emitter by putting it in a circle. But, like I said,
but why is that cheating? I mean, that's the way we measure all relative speeds. As I say, when the car is moving on the motorway at 50 miles an hour, and you are moving towards it at 50 miles an hour, you're measuring your relative speeds. You're not changing anything to do with the actual progression of that other motor car. You're measuring the relative speed relative to yourself.
Well, to the ground in that case. But typically, I'm saying it's just cheap because in order to accurately measure speed, you wouldn't want the distance between your measuring points A and B to be varying, right? If I was trying to measure the speed of anything going between my hands and my hands are going like this, then it's like that's not a legal measurement. You couldn't possibly make any sense of that, right? If you want to keep the distance fixed, right? Because you got to keep something fixed in order to measure.
No. That's what relative speed means. The distance between the object is actually varying. That's precisely what relative speed means.
Yeah, but I guess we're talking about, say, the speed of light, which we're trying. The question here, I guess, is whether the speed of light is actually measured as a constant or not a constant. In the comments, some people, I think, is asking, and I've also asked, what actual experiments have been done here? I just want to see a clean experiment where we have someone measuring the speed of light between points A and B, and then measuring that against the same exact setup, except moving at 100 miles an hour, and then showing that both of these guys measured the same speed of C. Now, I don't know that I've ever actually seen that experiment, right? We seem to have an awful lot of faith in that in relativity, but I could be wrong, but I've never actually seen any clean experiment like that. I mean, have you seen any clean experiment like that?
No, no. I mean, this is based on an interpretation, really.
It's like one of these things where
It's really starting actually from the principle
that relatively is so well
rather than deriving it.
that instead of actually doing actual experiments to confirm it, they just confirm it just because that's what the theory says, which is, of course, completely circular, right? I mean, one of the problems may be that we have a hard time measuring, say, the one-way speed of light, right? You have Veritasium saying it can't be done. In principle, can't be done. And, I sent you my little paper. I talked to ChatGPT about this. And, theoretically, using GPS, and one of the main operating principles of GPS is the ability to synchronize clocks on the Earth so that they all tick exactly the same, right? So that's virtually the thing that Veritasium was saying couldn't be done. You couldn't synchronize clocks. And Einstein is using this crazy Einstein synchronization by sending light waves in opposite directions in order to synchronize clocks. And that's crazy. That's relying on the very thing that you're trying to test. It'd be much easier to synchronize clocks like they do in the old army movies where everyone brings their wristwatches together and say, it's 12 o'clock. And then they go off to the various things and conduct their battle plans according to their synchronized watches. But I think that's kind of crazy.
There are a lot of comments, sort of related to this. One or two people seem to be on my line of thought, like Professor Halem, for example, and but I think people like Eric are taking issue to a certain extent. And
yeah, let's hear for some of the people. I see James is waving his hand, so let's go ahead and see what James has to say here.
Hello. If the notebooks are in the quadrature work, you mentioned that there were a large number of observations recorded. Why can't these be pumped into a spreadsheet and we do a two-sample mean test? Also, one can evaluate the quality of the data by looking at the distribution of each sample, both approaching the Jupiter and moving away from Jupiter, and so that you made the statement that these documents have all of these numbers. I'm a little surprised that the Statistics 101 was not applied here.
Yes, I think those are very good points, Jim. And I would think that it would make a very interesting research project. I don't know if anybody has done it. I don't even know. I haven't, I'm sorry to say, but I haven't got to the stage of establishing whether these notebooks can be obtained and can be downloaded. I don't know anything about that. Some of the
I see.
The diagram of some of the observations is just some information I got maybe from Wikipedia or something like that. That these are some of the notebooks. I don't know, but that would be very interesting because you've hit the nail on the head to a certain extent, if I may say, in indicating that when I analyzed these very early experiments, I just said, look, they appeared to get some sort of difference. I haven't indicated whether it's statistical, and I would say if you assume that what I'm saying is true, that you can do a sort of a hydrodynamic type analysis on it, they should have got a difference, and it would have been of the order of plus or minus 15 seconds. If you assume that special relativity is correct, it would have been absolutely zero. But I didn't give any results as to say who's right and who's wrong. It would be a very interesting experiment, research project, I say, to do.
Well, let me know if these numbers are available. We have two sets of numbers apparently, and it's just a matter of the clerical work to type them into a statistical database and do some statistics on them. Even just looking at the distribution of each of the two samples, going toward or away from Jupiter in the quadrature model you talked about, one can get an idea of how much outliers or error there might be in data collection, as it were, or just simple mistakes, as it were, in recording values or whatever explanation there might be. But one could back up your conclusion with an actual, these are statistically significant differences. And if there are you mentioned there was a large number of values and they took the average, that means that's the ordinary word for mean in statistics, MEAN, mean. This could be looked at, and I think it would bolster your argument, as it were. And in fact, that would be an important publication.
Yeah, and you, if I may extrapolate a bit from what you're saying, you might be willing to help if we ever got the data in that.
Yes, I would. Sure. I mean, James, it's just a matter of how many hours does it take to enter the data into a spreadsheet or a database, that whatever you're using. I write my own statistics program, so this would be relatively easy to do.
The only thing is, at the risk of appearing to be a little cynical, one might say there are a lot of data available to establish the difference in speed of light dependent upon observer motion towards or away. And they're explained away by the mainstream in certain ways. Now, I imagine that were one to do this very detailed experiment and research project and get a statistical difference, say, yes, look, there is a difference. The mainstream would probably bring in one of their arguments, and they would say, oh, yeah, but in one case, the distance is reducing because you're moving towards the source. And in another case, the distance is increasing because you're moving away from the source. And therefore, in the first case, it'll be a little earlier, and the other case will be a little later. Forgetting about that is only from the point of view of somebody in outer space, outside of the observation frame. So, in other words, they use that excuse to explain the Sagnac experiment or the Michelson-Gale experiment already, which we know, they're modern experiments to pretty high accuracy. And they use that excuse. They're not convinced by that. That's statistically significant. In fact, there was a very small difference in the Michelson-Gale series of observations. And that was a bit of a puzzle at one time. The average was 0.230 fringes, but that has been laterally explained as a correction one has to make for gravitational locking onto the sun and the moon, which will change this very, very slightly the non-dragging, if you like, of the ether, the slippage of the Earth through the fixed ether.
Okay, well, thank you.
Yeah, I agree with all that, but you could cynically say, would it be worth the candle? What are you trying to prove? We have evidence already. Well, I claim you have plenty of evidence to show that the speed of light is not independent of the speed of the observer. That is
but independent of the speed of the source.
It is independent of the speed. We have evidence for that as well. Yeah.
Okay, that clarifies. Thank you very much.
Well, thank you very much for your point.
Done a wonderful analysis here. Thank you.
Well, thank you very much. Thank you.
Yeah, I think it's interesting that so one of your main points is that speed of light can be measured as not constant, but only with respect to, say, the observer. So that's kind of your prediction, I guess. If we could propose an experiment, that's what you would do. You would see because that was your last screen saying that if you did measure the speed of light of the moving observer.
I'm relying very much. I'm relying very much upon there being a medium of transmission which produces these waves. Call it an ether or call it a medium or whatever you want to call it. I haven't used the term quantum foam because I've steered away from relativistic and quantum terminology in this lecture. It's totally classical. I almost imagine that had there been no sort of 20th century science, you would have had some person following Kelvin or Maxwell or McCulloch or something giving a similar talk to the one I've given. But it required sort of a dismissal of a lot of the orthodoxy that we've come to believe now. But I take a medium, to be essential. And if you have the source, which is giving rise to electromagnetic variations which produce a wave, well, it doesn't matter how that source is moving through the medium. If it did, you'd have a ballistic type system. You'd have like if a cannon is actually moving at 10 miles per hour and it shoots a ball, well, you get the addition of the two speeds. That's the Ritz hypothesis, the Ritz hypothesis. And actually, one of the disagreements I have with Alfred O'Reilly is that he seems to accept a Ritz hypothesis, whereas I don't. I would think it doesn't apply in the case of the ether. It's a bit more like water waves or waves in air. But if you have a wave which is actually produced there, and if you're moving towards, you remember I gave the expressions for the Lorentz transformations. No, sorry, the Doppler transformations. If you're moving towards that wave, in the ether, well, the frequency is changing. You're getting a Doppler shift, but the wavelength is compensated because the speed is changing. You're measuring a different speed.
Yeah, so we've got some questions here. So, the basic question is, what accounts for the possible differences in measuring C, though? Would the velocity of the light source add to the velocity of its actual motion? I think you're trying to address that.
No, well, that's the ballistic effect again.
I mean, there are definitely some.
No. Well, I don't accept the Ritz hypothesis. I think the easy explanation of all the experiments we have, and indeed the theory which I gave you an inkling of, is not to accept that the velocity of the light source adds to the velocity of the actual motion.
But it's different. So, I just...
Because unlike, say, a projectile, unlike a projectile, like a photon which is being projected in an empty space, you have something which is captured in a medium. It's a medium which is giving rise to these waves, and it's effectively captured by that. It's not a ballistic system like a projectile.
Yeah, but curiously, we do get these differences in the measurement of the velocity of the seas. For example, they did an experiment where they transmitted from, say, the West Coast to the East Coast. And so you can measure how long it takes for it to go that direction. And then they measured the same way going from the East Coast to the West Coast. Yeah. And you know what? The time, it's different. It takes a different amount of time for it to go the direction. So, some people like Stephen Giftwood claim that, well, see, there we go. That speed of light is not constant, right? That's definitely something that's been measured. But then again...
So that's the Sagnac correction.
Yes, to your
that's
point,
a Sagnac correction. And where one in outer space looking down at that, one would say, well, in one case the Earth is moving with the light and is actually adding to it, and another, sorry, it's subtracting, but yeah, adding to it from the point of view of outer space. You have the two speeds for adding, and in the other case, when it's moving the other way, it's moving against it, and it's sort of subtracting from it. But if one was actually on the Earth, where measurements are normally made, one would say this is changing, yes, because when you're moving with the Earth, the speed relative to the Earth is actually diminishing, and when you're moving against the spin of the Earth relative to the Earth, it's actually increasing because you have the addition of the two speeds. So it's really a question of which frame of reference you take to decide whether the speed is changing or whether the distance is changing.
Then we have a comment here.
But to say that the speed is not changing is like saying that this motor car, which is going down the highway at 50 miles an hour, cannot change its speed because it's the tires are doing a constant speed relative to the road. Correct? No matter what a V plus minus C experiment shows, the relativist automatically goes into psychosis using relativistic formulas with length contraction time. There's no other possibility. Well, that, I suppose that's what I'm saying, except he's a little more emotional than I am, I hope. But yeah, I mean, I agree. The relativist is using, I don't know if it's a psychosis, but he's using explanations to save his hypothesis.
Now, I had an interesting thought that, if we were actually able to do this experiment cleanly with an experiment in moving frame versus one stationary, that the relativists would say, and I think they may be correct, that that even the moving observer would still observe the same speed. Your last slide said, the light is overtaking them at 98,000 miles per hour, but yet they would still measure the speed of light at being 186,000 miles per hour. And the reason that would be is because the clock on the moving frame is going to be running slower. So therefore, you change your yardstick on time so that it's measured the same. But if they were to be using, like, if we were able to come up with a universal synchronized clock, which is the same everywhere, regardless of what frame you're in, then you would immediately see that you would see the slower speed of light. They would measure 9,800 miles an hour if they were using the same clock as the stationary guys. But once again, it's kind of a cheat, and I think it's very kind of hard to that's why it's so irksome, this whole relativity thing, and while the relativists are so make things so confused, because if you change your standards of time, then you cannot make relative comparisons, right? If you're running a sprint between two people and the referees are using two different clocks, then how can you make any comparison between those two? It's like the first guy won, but he said the other guy would say he lost because he took 60 seconds to cross the line and the other guy took a minute and a half, even though that guy clearly finished first because the other guy's clock was wrong. So you can't use different time bases to measure the same thing. I mean, what do you think of that?
Well, I was a little pedantic, ab uno disque mines. So if you take the one example, you are forced to say that if you have this person who is running at half the speed of light and you shine a light then at him and it overtakes him by half the speed of light, okay, that he will observe that light overtakes him at the speed of light, not half the speed of light. You are forced to say that if you if you take this absolute consistency and constancy. I don't think you believe that, Franklin. I'm not sure, but you're
Yeah.
forced to do that. I said, and I quoted O'Reilly to say it not only seemed to be nonsense, but actually was nonsense.
But my point was, it's that the difficulty with how you do the measurement, right? When you do the measurement, you're dealing with particular clocks, you're dealing with particular rulers, and it's clear that the clocks aren't reliable because the clock tick depends on how fast it's going. We know that. So and like GPS has to go through all these humongous gyrations to erase those differences, because the clocks and GPS are not only going at different speeds, they're going in opposite directions to each other, and GPS has incredible complicated number of corrections just to make it so that all clocks on the surface of the earth appear to be ticking at the same time. So does GPS use relativity? It's like, I think we would agree that the engineers kind of just threw all that out, and people like Ron Hatch just said, let's just make it work. Okay, let's just do what it takes. And, that's why people like Ronald Hatch, will say controversial things that no, we have to kind of throw out relativity. We have to, when you see the speed of light is a constant, I mean, what the heck does that mean, right? Constant compared to what? Let's see, I think we have some other,
Yes.
It's about like the MMX. And for example, the Michelson-Morley experiment was used to establish that the speed of light is constant. I'm not sure if that's. So what are your thoughts on the Michelson-Morley interferometer, and compare it against the other experiment that you actually did, what was like the Michelson-Gale? I think people get those confused.
Yeah, well, I mean, we could give a talk on that, but there are a number of fundamental differences. First, and I think there was one question, it might have been even you, I don't know, somebody posted this up, Franklin. What's the difference between first order and second order? You see, the Sagnac, well, the Michelson-Morley type experiment is basically concerned with the difference between to and fro operations. So in other words, you're moving a ray of light to an area and it's going to be reflected back. And then you do the same with another ray, which is at right angle, say, to it. And you look at the difference. So it's effectively based on analyzing the to and fro motion. Now, if you work out the equations, it's very elementary. You find that depends upon v squared over c squared. So it's a second order effect. And remember, v is the Earth's speed through the ether, which is something like 30 kilometers per second.
So the second order part, that's
the speed of light, 300
squared. Is that what makes it second order? It's v squared.
It's that squared, yeah. It's squared.
Okay, so that's
right. That's what second order means, yeah. Now, a skilled experimenter, if he knew nothing about light and he wasn't interested, he would say you shouldn't do that. You should actually take the difference. You should have a ray going in one way, just not returning, going in one way, and a ray going in the opposite way. And you should compare the times. You should look at the difference in times. So in other words, that's what the quadrature experiments of Romer do, and that's what Sagnac does, and that's what the MG, Michelson-Gale, does. And if you work out the equations, it depends only on first order, which is V over C. So, you can work that out. It's the accuracy required is it's huge. It's 10 to the power of 6 or something. The accuracy required for a Michelson-Gale type apparatus. And that's why the MG showed up an effect which the MMX didn't. Okay, the MM didn't, and the MG did. Now, I put in parentheses, rather, on one of the slides that actually in 1979, the Brie Hall, using an Michelson-Morley, not a Michelson-Gayle, a Michelson-Morley setup, actually detected the speed of the Earth through the ether. But this required very, very sensitive equipment. It's like these cavity resonators with lasers and analyzing the beat frequency using the Fabry-Perot interferometer. Very, very complex experiments. And actually, at the end of the day, they say it proved relativity, it proved nonsense. But actually, if you look at their own data, you show, well, I say, I've forgotten the gent who first looked at this. He's an English physicist. Aspin did it first. He found this signal actually related to the rotation of the Earth. So that's the fundamental difference between the two. If you were starting from scratch, from a blank slate, you would do a different experiment instead of a to and fro experiment, because the to and fro experiment requires equipment of such great accuracy to determine. Now, that's the first difference. Secondly, it appears from the experiment and from detailed experiments and from others using cavity resonators and things like the Truton Noble experiment, which used the charge variation on a capacitor is moving through the ether, that there's virtually no difference in fringe shift between the rays in the opposite direction. It's not zero, but it's very, very, very small. So in other words, Stokes, whose analysis or whose nomenclature I used a moment ago, Stokes was correct in saying that there's a drag, there's at least a partial drag of the ether by the Earth in its motion around the sun. And that's what gives rise to the Earth-centered inertial frame, because this is the frame on which we don't really notice non-inertial effects. We're on the Earth. We can jump up and we don't land in a different place, even though the Earth at our maybe the speed is going at nearly 1,000 miles an hour. We still land back at the same time because we're carried with the Earth. Same way, the ether is largely carried by the Earth. I think you used the expression yourself, Franklin, as a bubble or something like that. So that's true. It's not 100%. There are effects due to gravitational locking by the sun and the moon, but we do have slight effects. Now, the effect due to the spin of the Earth. Now, the spin of the Earth is very much less. It's only something like 300 or more meters per second. So it's very, very much less, but it's much less inertial, because you could work out the radius of it. The radius is the radius of the Earth spinning as against the radius of the Earth's orbit. So things like centripetal force and Coriolis forces, they become very much more important. And that's why we notice effects. For example, the weather patterns. We get atmospheric effects in the upper atmosphere, which are maybe not only due, but they are partly due, or they're exacerbated by the Earth's spinning. And we find, by the way, that we use this because the major launch pads for rockets are invariably located near the equator of the Earth. So they use the spin of the Earth to assist with the launching of the rocket. I'm just reading this. How is constant C nonsense? I don't mean to necessarily say that it isn't. What is your view? Yes. Well, Quest, I told you that taking the extreme example, that if C were constant and you had a runner who was going at half the speed of light, and you shot a light beam at him and it overtook him, he would still see it not going at c/2, but going at c. Well, that is nonsense. That is complete nonsense. You can work it out by simple algebra. I mean, even when the relativists talk about the space between objects which are moving towards each other becoming smaller, and the space between objects which are receding from each other becoming larger, and that determines any apparent non-constancy of c that we measure in things like Sagnac. Well, that can be applied to any kinematic system where you have objects moving relative to each other. The space between them is actually changing, and that's what determines within their own frames the variation in the speed of light. Sorry,
Yeah, so
the variation in the speed. If you have a ball moving towards you, it hits you with a certain speed, but if you're moving towards it, you get a bigger wallop, or if you're moving away, you would mitigate the speed at which it hits you on the head.
Yeah, so fundamentally, in the two-runner case, you would think that if the guy was measuring the speed and he's overcoming, that they should really measure the speed at 98,000 miles per second, right? That's what you're saying. that guy
93, yeah.
should only see that particular light beam overcoming him at 9,800. Although the relativists would say that when he measures it going past, that he would say, "Oh, that's 186,000 miles an hour," right?
Yeah.
See, now we could
Well,
actually experiment. I don't know that.
I mean, as I say, they explain things like the relative motion by saying the distance changes, but there is no pleading for one to understand how what you've just said applies. What I was told when I was first learning this in college, they said it's against common sense, but you just have to accept it and forget that time and space are what you think they might be. They warp in such strange ways that this is true, that the man will still, if he were going at the speed of light and then you shone another ray beside him, it wouldn't mean that the speed was zero because they were both going the same speed. He would still see it going at the speed of light. And c plus c doesn't equal 2c. It equals c.
Yep. Now, Dennis, he said he sent you some Chat GPT thing. I was wondering, Dennis, did you want to come up and talk to about that? Let's just see. Let's just bring up Dennis and see what he has to say.
Well, thank you. But I don't know how to bring things up in StreamYard. I sent the email to Ian just before the meeting started, and maybe he could bring it up. He has more skill in that.
Yeah. Okay. Yeah. I did see it coming in, but I didn't have time to read it, Denny. I could bring it up if you wish, but I'd have to share my screen.
Yeah, would you please do it?
Shall I do that, Franklin?
Yes.
Any other way, or I could send it. How else can I show it?
You can just share your screen, or Denny, you can just.
I'll bring it up and share my screen again. Shall I? Okay. What else? What else shall I do?
You can just share your.
Yeah, you could do it, Denny.
If you want to.
No, I don't know how to do it. I'm very,
Or Denny, you could just.
Can you see?
You could just tell us what's in the email.
No, so I'll do it.
Also, we've got.
It's a long
I think
thing.
you'll be interested in what.
Well, look, I'm going to bring it up now.
Yeah, we've got. If there's anybody else in the
I'll
green
bring it up now.
to speak, just wave your hand. I see we got Cornelius and Vladimir and Harry out there. So if you have any comments, please.
Actually, without having given sufficient attention to it, I would be a bit dismissive, Denny, because I think this AI business is probably just a lot of nonsense. It's just rehashing things which are on the web already, and there's no intelligence behind it. As I think David Hilster sent a memo out as well to that effect.
Yeah, I know, but I think if you read this, it'll be interesting.
Here it is. Can you? It's loading now. Wait a minute. Can you see it there?
Yeah.
Yes.
Yeah. Now scroll down.
Can you see it?
Yes, we can see
Scroll
it.
down to where?
Up here at the upper
Further.
right, what I asked, and then the answer is down below. So what I asked was,
Yeah, but you've asked a number of things.
Today, the proponents of special relativity
do not prove
it's impossible
that it's impossible to measure the
one-way
one-way speed of light. Instead, they assume it. Is this true? Well, I say it isn't true. Do you want to see what ChatGPT says?
Yeah.
Yes, your statement on the fundamental aspect of theory of relativity and the nature of light. Let's break it down. One-way speed of light. The one-way speed of light refers to the speed of light as travel from A to B without any intermediate. Two-way speed of light it takes time. Mirror back. Yeah, this is commonly okay. The assumptions in special relativity, assumption of constancy, special relativity.
Okay,
I mean, Denny, this is just rehashing what's on the web. Is there any specific that you want to bring? Shall I go down to the conclusion? See, why it's assumed, not proven.
Keep scrolling and you'll come to a conclusion.
Conclusion. In summary, while proponents of special relativity do not claim to have proven the one-way speed of light can be measured directly, I think he means cannot be measured directly. They operate under the assumption that it is constant based on the robust experimental evidence supporting the two-way speed of light. This assumption is a fundamental aspect of the theory, leading to its wide acceptance and development in modern physics. Yeah, well, he's conceding that they're extrapolating from having measured the two-way speed of light, and they're assuming the one-way speed of light.
They assume that it's impossible to measure, and because by assumption, it's impossible to measure. Now, scroll a little bit further. Now, here's my next statement here on the right.
But the GPS
with a synchronization of clocks has been verified with extremely high accuracy. Is this true? Yes, you are correct. And it goes on.
That and has been verified to operate with extremely high accuracy. Let's explore how GPS over the importance of clocks and how it relates to the concept of special relativity.
Now you can scroll down to the conclusion. You can scroll down to the conclusion.
Conclusion. In summary, while GPS does involve advanced synchronization of clocks and has been verified to operate with high accuracy, it also fundamentally relies on the principles of special and general relativity. The need to account for relativistic time dilation effects when synchronizing the clocks of satellites and receivers is a key aspect of its functionality. This highlights how modern technology effectively incorporates and validates theoretical physics and practical. Well, I contest that, as many people might, because they're confusing clock retardation effects owing to velocity, and also atomic clock retardation or advance actually effects owing to gravitational potential with special and general relativity. It's true that the equations
right. I would agree with that. I would agree with that. Now, here's my next question. But then, why can't we? Why can't we synchronize the clocks at A and B using GPS and then send a pulse of light at a certain time using the clock at A, and then further measure the time of reception at B and take the difference of the two and then divide by the distance from A to B by this difference to get the one-way speed of light from A to B? And they say, your question has raised an interesting point. Scroll down to the conclusion. There we go.
In summary, while GPS provides the means to achieve highly accurate synchronization of clocks, any attempt to measure the one-way speed of light using these synchronized clocks ultimately leads back to the foundational assumptions of special relativity. The relativity of simultaneity complicates any straightforward measurements, as the synchronization process itself relies on the assumption that the speed of light is constant. Yes, but that's right. Thus, a truly independent measurement of the one-way speed of light remains elusive due to the very nature of how we synchronize time and measure distances in the context of relativity.
Yeah, now here I asked him again. I said, but if the GPS is as accurate as you say, shouldn't the conclusion be that then SRT's assumption that the one-way speed of light cannot be measured be evidently incorrect? Now scroll down to the conclusion.
There. In conclusion,
Okay,
while
here we
GPS
go.
technology...
Can you read that?
Yeah, I can read it if you wish. In conclusion, while GPS
Go ahead.
technology provides highly accurate synchronization and demonstrates the practical application of relativistic principles, it does not inherently invalidate the assumption that the one-way speed of light cannot be independently measured without assumptions. The challenge lies in the dependence on the synchronization method and the implications of the relativity of simultaneity. Thus, special relativity remains a robust framework for understanding the nature of light and time, even as discussions about the one-way speed of light continue in both scientific and philosophical realms.
Okay, now my next one is, you say GPS provides highly accurate timekeeping and synchronization of clocks. However, the synchronization achieved through GPS is based on the assumption the speed of light is constant in all inertial frames, as postulated by Einstein's theory of relativity. However, GPS does not rely on the assumption that the speed of light is the same constant C in all reference frames, because it denies that cesium clocks do not always keep the same time, but rather says these clocks have their time rate adjusted slower or faster depending on how deep they are in a gravitational field and how fast they are going. Okay, scroll down to
the conclusion.
Yeah.
In summary, GPS technology.
Here we go.
Shall I read it? Application of both special and general relativity, accounting for relativistic effects due to speed and gravity. However, the synchronization of clocks using GPS still relies on the assumption that the speed of light is constant when determining distances and positions. The challenge of measuring the one-way speed of light independently arises from the dependence on the choice of synchronization method, which leads back to the foundational assumptions of special relativity. Thus, while GPS demonstrates the practical application of these theories, it does not provide a direct measurement of the one-way speed of light that is free from assumptions. You see, I would say there are two major errors here. The first one you agreed with, that they're mistaking clock variation with time dilation and gravitational potential with special relativity. And the second thing is to be blunt about it, that GPS uses a correction for the spin of the Earth on the, when we're measuring, making measurements on the Earth, which contradict relativity, because the speed of the signal has to be changed to account for the spin of the Earth, which, if special relativity were correct, would not be the case.
Yeah. Now here's my next question. Nothing is free from assumptions, but the GPS assumption that certain clocks all keep the same assumption that cesium clocks all keep the same time when they are wherever they are, and no matter how fast they are going, leads to the rate of time passing being different in different places in the universe, which then results in many paradoxes. But using the GPS instead of the special and general relativity does not result in any paradoxes, so far anyway. Now, scroll down to the conclusion.
Okay.
All right, we only have time for one more conclusion because our time is up, but let's read this conclusion.
Okay.
I'll be quick. In conclusion, while GPS technology relies on assumptions about timekeeping and synchronization, it effectively incorporates the principles of special general relativity, providing practical solutions without leading to paradoxes in its implication. The understanding of time as relative rather than absolute is key to reconciling these assumptions with the operation of GPS. While there are philosophical debates surrounding the implications of these theories, GPS serves as a robust tool that operates successfully within the framework of relativity, demonstrating the power of empirical science to navigate complex theoretical landscapes. The ongoing exploration of time, space, and the nature of reality continues to challenge our intuitions, but GPS illustrates how these concepts can be applied practically without conflict in everyday technology.
All right.
Well,
Well,
I disagree with that, really, I suppose. I better take
all
some
right.
water.
Well, we are unfortunately out of time. So, Ian, I'll let you take us out with whatever conclusions you would like to make. And that will do it for this episode of the John Chappell Natural Philosophy Society.
I've stopped sharing now. All I have to do is get back. Let's see.
Yeah, just go ahead.
Okay,
Give us your conclusion.
I'm back. Thank you very much. Sorry, Franklin?
Just go ahead and give us your conclusion.
Okay. Can you hear me? Oh, okay. Well, thank you very much for your attention and the great questions. There are so many questions here that really I haven't been able to deal with. We can look at them and come back to them at a later stage. I think my conclusion basically is that there are bland comments put out about the speed of light. Oh, it's constant. And what do you mean by that? The special theory of relativity says so. I've given, and the two-way speed of light is the only feasible means of measurement. Well, I've given, so I believe, some examples going back to hundreds of years to illustrate that is not the case. In fact, maybe the one-way speed of light was the first to be measured. And we've really been confused a bit by modern relativistic ideas, which poo-poo that and say everything is two-way. And if you come to home in on the situation, you actually get a nonsensical conclusion. And that's what I was trying to prove by giving this one extreme example. But I would say that we've proved in many ways that light is a wave, and electromagnetic radiation is a wave, which is propagated in the same way as other waveforms. One can use the same classical equations which were used in hydrodynamics and aerodynamics. And one has experimental evidence to show that although a moving source in the ether does not give rise to a ballistic effect where the speed of the moving source is added to the speed of the radiation, and therefore it's basically constant, it's independent of that. Observer motion towards or away from a source of light will affect the observed speed of that electromagnetic radiation relative to the observer, and therefore it's of the utmost importance that we make a distinction with regard to source movement and observer movement, and stop making bland statements about the speed of light being constant. But thank you very much for your attention. I look forward to addressing more of these issues in more depth.